So thank you so much, and thank you guys all for coming. It is absolutely a pleasure to be here. So today I'm going to talk about the formation of structure in the cosmos. And what do I mean by this? So I kind of wanted to give an overall perspective. So we got to go back in time. So if you go back to some caves in France, you'll find that there are paintings on these cave walls. And these paintings have various things. There are cows and bulls. But there are also these strange dots that don't quite look random. They seem to have some type of a pattern. That's one there. And there's another one there. And in fact, this is a picture, this is an actual sky chart of the Pleiades constellation. It's a star cluster that has several bright stars and a bunch of faint stars associated with it. And as you can see, these big dots represent the brightest stars in that cluster. They look very, very similar to this structure here, which was painted on this cave wall. And in fact, if you zoom out a little more, this other structure here looks very much like Orion's belt. And the Pleiades is just up there in the corner. And you can see this is the eye of this bull, nominally. The point here is that we're really wired to recognize structure, and that for thousands and thousands of years, we have been trying to look at the heavens and understand what structures are there and what those structures mean. And we really see structures everywhere. So now we have better telescopes, and we have more than just our eyes to look at things. And so what do the stars actually look like? So these are clusters of stars. Here I'm just showing the scale of these images. This is 2 light years across, 65 light years across, and 150 light years across. And you can see these clusters kind of have some type of a shape. They sort of look like balls of stars. You can see in the center, there seems to be a higher density of stars than in the exterior. Maybe you can even see in this picture there are different colors of the stars. Those different colors represent different temperatures and different masses of stars. And we see, okay, so this looks sort of like a fuzzball of stars at some level. And then going out further to galaxies, we also see structure in the galaxies. But now this structure looks quite different. So now we're going out to a much larger scale, 50,000 light years across. And this is the famous Sombrero galaxy. You've got the Whirlpool galaxy, a few different pictures there. But these look very, very different from those star clusters. Well, some of them do anyway. You've got these spiral galaxies that have a particular type of structure. And then you've got these other galaxies that look kind of spherical, quasi-spherical, and very red. So you have these spiral galaxies that have star formation going on in them, and you've got these red galaxies that don't seem to have very much star formation going on in them. So what is that structure about? And now if you go to even larger scales, so not just clusters of stars, but clusters of galaxies themselves, this is now 1 million light years across. These are images of two clusters of galaxies. Again, you see this structure. So you see that there are sort of a concentration of galaxies in the very center of this cluster here. This one looks a little bit more disturbed. But I think the real question is, where does this stop? So if you go to the largest scales that we can observe, the cosmic microwave background, you see another type of structure. So now we're talking about enormous scales. This is the entire sort of observable universe in some sense. And you see these temperature fluctuations. I know you've heard a little bit about the cosmic microwave background in this lecture series before, and I'll talk more about it later. But the point is that this structure there's these different structures on different physical scales. And the real question that motivates a lot of astrophysicists is there really any sensible relationship between these different structures on different scales, and can we discern that? Now, of course, cosmos from the Greek means harmony and order, and really we're trying to understand what the order is in the universe, and using these probes, try to figure out those rules. So my two favorite stories, my two favorite cosmic stories, are really the story of the expansion of the universe and the story of the existence of black holes. Now, really, these are actually just two separate solutions of Einstein's field equations. But I think they represent very different ways we've interrogated the universe over the last few hundred years, and it's a very exciting time in both of these areas. So I'm going to go over at least some elements of both of these stories for you today. So for part one, I'm going to talk about the largest scale cosmic structures. So how do large scale structures form? how did we learn this? How did we learn this process? And what are we still learning about this process? So I'm just going to go ahead and give you the answer. How did this structure form? We know the answer. We know that there were small perturbations in the early universe, and those perturbations grew, and over time they collapsed, they went nonlinear, they grew into this filament void structure of dark matter, which then is traced by the galaxies that we see. So this is the universe at an age of only 300,000 years, and this is this lumpy galaxy distribution at 14 billion years. And even though the density contrast here is much, 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 much larger than the density contrast of any little patch there, we can show how these fluctuations turn into these galaxies. And so that's sort of the answer. This is the answer to how structure formation happens, but how did we come to this, and what does it actually mean? So going back to the 20s, what did the universe look like? Okay, so in 1915, of course, we're at the 100-year anniversary of general relativity. Einstein publishes his famous theory of gravity, and about a month later, there's a solution for these field equations. That is the Schwarzschild solution, which is essentially just a point charge solution. Now, why did Einstein's theory become so popular so fast? And I think the reason that it became so popular so fast is because it resolved two important anomalies that people had been struggling with for decades. One anomaly was they observed that Mercury's perihelion precessed, and they couldn't explain that with Newtonian gravity. And the other was the deflection of light. And in 1919, Arthur Eddington makes this critical test measuring with solar eclipses the deflection of light of stars. And I think that's really the point where people think, okay, yes, this is really what's happening. It's kind of interesting in retrospect, though, because these aren't, at least now we kind of have some sense of the sort of grandeur of general relativity. These aren't really the best, juiciest predictions of general relativity, right? I mean, okay, the planets are orbiting a little bit different, but you also have things like black holes and cosmology in there. So it's kind of just shows the richness of the theory. Now that was what was happening in the sort of gravity and physics community. And in the astrophysics community, there was this great debate raging. And that debate really centered on what was the size of the galaxy, the Milky Way galaxy, and what was the nature of the spiral nebulae. So people were observing, they were observing the Milky Way, they were observing stars in the Milky Way, they were observing planetary nebulae in the Milky Way. And then they observed these little smudges. They didn't quite know what they were. Were they gas clouds that were being illuminated? What were they? They didn't have images like the ones I showed you before. They had images like this because they were using photographic plates. So they were kind of these blurry images, and really wasn't clear what they were. Of course, now we have beautiful images from the Hubble Space Telescope that resolve individual stars in these types of galaxies. But at the time, they were working with much worse data. And so you have this great debate, which is between Curtis and Shapley. And I think the real essence of the debate was really about the scale of the universe. So nominally, Curtis argued that the Milky Way was small and that the spiral nebulae were external to the Milky Way. And Shapley thought the Milky Way was large, similar to the size we know it is today, and that the spiral nebulae couldn't possibly be external, significantly external to the Milky Way or similar to the Milky Way. Why? Because if either one of them had accepted the other's size of the Milky Way, it would have implied a size of the universe that was just unfathomably large at that time. So, so they were both sort of right and sort of wrong, which is often the case. But how was this actually resolved? So, of course, this is the famous plate that ended this debate. Here is a picture of, this is a plate taken on the 60-inch telescope. Actually, this is not the plate for this particular debate, but it's the same galaxy. So you see this spiral nebulae, M31, and this is a plate taken by Edwin Hubble. This var up there is indicating a special type of variable star. So the reason that we didn't know the distances to these galaxies is because we didn't have absolute luminosities. So we didn't know if the galaxy was very, very bright and nearby, or very, very bright and far away, or very dim and nearby. And there weren't really good handles on that, but Henrietta Leavitt came up with a relationship between the period of certain variable stars and their luminosity, their absolute luminosity. And that law allowed Edwin Hubble to actually measure the distances to these external nebulae. And he found in his paper in 23, I think, he found the corresponding distance was about 285,000 parsecs. You see he crossed out, he originally thought that star was a novae, but it turned out to be this other type of variable. So he crosses out the n and writes var, because now he knows he can get a distance to this object. So of course, this puts the spiral nebulae very far outside of the Milky Way. And at the same time, that's in this sort of astrophysics world where people are really trying to struggle with very Newtonian questions. What is the mass of that thing? How far away is it? How fast is it going? Whereas in the physics community and in the mathematical community, they're really struggling with these other issues. So of course, in 1922, you have another exact solution to Einstein's field equations. And this is the Friedmann equation. And this is the first exact dynamical solution to the field equations, assuming homogeneity and isotropy. So homogeneity, there's no preferred location in the universe, and isotropy, there's no preferred direction in the universe. So this is pretty important, because when Friedmann is working out the metric and he's working out his solutions, and I just write his solution there, he recognizes that there's no stable static solution. The solutions expand or contract. And that's just shown here. You have a dot over a. A here is the scale factor, and that just shows how the distance scales with time. Now at similar time in 27, Henri Lemaitre proposes an expanding universe as well, but here he's thinking again about these nebulae. So Hubble has measured velocities. There are literature velocities actually for the spiral nebulae. And Lemaitre is thinking about these velocities without knowing all the distances. He's thinking about the velocities, and he similarly comes to this same solution for the field equations. And of course, in this space, the velocity as a function of time is given by what we now call the Hubble parameter times the distance, right? So this is the velocity-distance relation in that picture, right? In 1931, I should say, Lemaitre proposes the Big Bang. This is this primeval atom theory, which is just extremely prescient. He's thinking about, I've got this solution. The solution is dynamical. It's either expanding or contracting. He sees these velocities are expanding, and he's thinking, OK, what does this actually mean? So just really following the mathematics, but with a sense of what the sort of observational state of play is. And of course, in 1929, with the brand new telescope, Carnegie's 100-inch telescope on Mount Wilson, Edwin Hubble actually determines this magnitude redshift relation. So here we're just showing distance versus velocity. This is taken from his 1929 paper. And of course, you see this relationship, and that looks a lot like this equation. And of course, this term is now called the Hubble parameter because Hubble first determined it. Interestingly, Hubble did not believe in the expansion of the universe. He always called it the magnitude redshift relation, preferring to stay agnostic about what it actually meant. Of course, here's a more modern version. This is from the Carnegie Hubble program. Here is now redshift. Hubble didn't have those distances right. He underestimated the distances to the spiral nebulae, so he got a Hubble constant about a factor of 10 higher than the real value. But anyway, here people have now measured this very precisely, and of course, this is one of the keystone parameters in cosmology. OK, but just going back to this Big Bang picture, once Hubble measures the expansion, OK, then this Friedmann-Lemaitre stuff seems really on solid ground. And what does it actually imply? So now you've got this Big Bang, this hot Big Bang. You reverse the arrow of time. Right? You've got an expanding universe, and then you contract that universe, and it tells you immediately that you have a very hot, very dense plasma at the beginning of time, this Big Bang singularity nominally. So this predicts Hubble's expansion. It actually also predicts the very early phases of the universe, so this hot radiation that we now know is the cosmic microwave background, and it also predicts the nucleosynthesis of light elements. So think about this. When you go back to high densities and high temperatures, right, you start to get fusion reactions, just like in the centers of stars, you get fusion reactions. And that same process is happening now in the early universe, and that's you're synthesizing heavier elements than hydrogen in the Big Bang itself. And both the prediction of this hot radiation left over from the Big Bang, as well as the prediction of nucleosynthesis, and this is just the density of regular matter as a function of relative to hydrogen. This is the curve for lithium, for helium, deuterium, and that's helium-4. And this is the currently measured value from the cosmic microwave background. So these are the consequences of the Big Bang picture, but this is super contentious. People argued about this for decades because, honestly, the expansion of the universe is something people are very uncomfortable with. Hubble didn't really believe it, and many people felt it was unpleasant. In fact, when Einstein originally found the solution, he also thought it was unpleasant, which is why he put cosmological constant in. So you have this Big Bang picture, and in this Big Bang picture, the age of the universe is finite, and the universe is cooling with time. And you have this steady state picture in which the age of the universe is not, the universe is something that has always existed and always will exist, and there's this continuous creation of matter that keeps it in this steady state. So this was very much debated. And what ended, so I should say that the big proponents of this steady state picture, actually the people who gave the name Big Bang to Lemaitre's primeval atom was Fred Hoyle. And these guys were also thinking about nucleosynthesis, but they really felt that nucleosynthesis had to occur in the interior of stars and in supernova explosions where you had high velocities and high temperatures and high densities. And in their very famous paper in 1957, they go through how you produce the periodic table, different aspects of the periodic table, just through fusion reactions in stars. But there's a problem. So what's the problem? The problem is that helium goes away inside stars and in supernovae. So the observational fact that people are observing this high helium, you burn to helium, then you burn again, you burn to carbon, you keep on going, you keep burning. So when people observed that there was always sort of a lower limit to the helium abundance in stars of about 24%, so a really sizable lower limit, it really kind of put a kink in this whole picture. Where was this helium coming from? It couldn't really be coming from this picture, which so nicely, and is still just a seminal work in nucleosynthesis, it produced all these other elements. Okay, so this is of course, the discovery in 1965 by Penzias and Wilson of the microwave background at Bell Labs. This was just the absolute, at this point, it just killed the steady state idea. It was Big Bang or bust from then on. Essentially, I think you guys all know this story, but they were doing this experiment, really trying to interrogate communication satellites. And they kept on finding that they couldn't get below this noise floor. No matter what they did, they scraped all the bird poop off of their machine, and they still found that they had all of this noise. They actually comment on that in their paper. So they just had this excess of 3K, and it's seemingly coming from everywhere, and they couldn't get rid of it. And of course, this is the extra radiation left over from the Big Bang. And in a companion paper to Penzias and Wilson's paper by Dickey, they describe exactly how this radiation should look. Now, there were two things that they measured here. So they measured a value for the temperature, and they measured that it was smooth. And the smoothness is critical. So the actual value of the temperature is very important because you have a cooling universe. So that value of the temperature tells you something about the dynamics of that universe going back in time. But the smoothness tells you something very different. So if you had an early universe with lots of perturbations, some sort of plasma where lots of wild things were happening, how did you get this same temperature in every direction you looked? So it was extremely smooth, and maybe people felt too smooth. But in fact, these imperfections are critical. And in work in the 70s done by Jim Peebles and collaborators, and also Harrison and Zeldovich, they recognized that the fluctuations in the CMB temperature was an incredibly important theoretical test of the cosmology. And here I'm just showing the amplitude of the amplitude of the brightness in the fluctuations, and this is now multiplied by 10 to the minus 5, because that's how smooth the cosmic microwave background is. This was the observational limit that they had, so they already knew back in 1970 how smooth, that the CMB was extremely smooth, and it just ruled out cosmological models immediately. And so then, well, then there's really the struggle. If the CMB is so smooth, how do you get this structure? Now, of course, one way to parameterize the CMB is to expand it in its spherical harmonics, and that's kind of the typical way we think about the CMB. And so this is just showing scale as showing the CMB power spectrum here. And you can just see from these different curves, you have different values of omega naught, and you have different values of omega lambda, where that's just the ratio of the energy density to the critical energy density at that time. This is at the average of 1200. And you can see that for different cosmological parameters, this spectrum of fluctuations moves around. So that is why, fundamentally, the cosmic microwave background is so sensitive to cosmological parameters, because if you measure this spectrum, you have this first peak tells you very clearly what sensitivity you have to the total matter density. So this issue of the isotropies are very important, but temperatures are one thing, but if you're like really a Newtonian kind of person, not really a quantum person, then like mass is what you care about. So I think the nicest way to think about the CMB fluctuations in terms of mass fluctuations is the Sachs-Wolf effect. So if you imagine a photon entering a gravitational well of a certain size, like a supercluster, okay, and the universe is expanding, then when that photon comes out of that well, right, it's going to have less energy than it gained on the way out, okay? So it actually changes the photon energy depending on what that mass fluctuation is. So that immediately gives you a correlation between the temperature fluctuation and the density fluctuations. And that's precisely what you need in order to make galaxies and clusters of galaxies. So the point here is that the amplitude and distribution of these temperature fluctuations is really the key to understanding the mass fluctuations. And then the mass fluctuations, once they're frozen in at the surface of less scattering, they grow into the galaxies we see today. And we can both calculate this process numerically and semi-analytically, and we can observe this process. So there's still a question, we're talking about perturbations and small fluctuations, and that makes sense when you're talking about sort of a perturbative idea, but galaxies have mass, they're things. And so how do you go from a perturbation, a little delta rho over rho, to an M, to a mass? And that's where this critical idea comes in, where imagine yourself on one of these fluctuations, right? At some point, as the universe is expanding and you're here, you're sort of in a locally closed universe. And that, you sort of detach from that flow, and then you become a thing unto yourself, not part of that Hubble expansion. And you can imagine, and there's a critical density that you can solve for where that notion of a spherical collapse occurs. And you imagine there are just these fluctuations in this overdensity in the density of the fluid. And when you go above that critical density, that's when we're going to call you a thing. In this case, a halo. We'll call you a halo of matter. Okay? And this idea was very critical for understanding how galaxies could form. So the first, you could do this analytically, but the first calculations of this really were numerical calculations where they tried to really say what the spectrum of mass was going to be from these initial perturbations. And this is this paper by Press and Schechter, and they show the distribution of what they called condensations, because they were thinking of these things condensing out of this fluid. They show the mass of these condensations as a function of expansion, and they show what fraction of their condensations are in each of these bins, and so they build up a mass function, a distribution of masses in this way. At the same time, you also have dark matter, which is gaining a lot of momentum. So people knew about dark matter from very early on. They were just looking at the motions, and the arguments in clusters are very similar to the arguments in galaxies, where you look at the rotation curves of galaxies. And the argument is just a very simple argument. You have some Keplerian rotation or some rotation, some virial velocity, and that should reflect some enclosed mass. And the values of the velocities that people were getting implied masses much larger than when they just added up the mass they could see. And so by the time that these calculations are being done in the early 70s, people are making measurements of these rotation curves. This is, of course, Vera Rubin, who's a pioneer in this work. And by the end of the 70s, it's pretty much accepted that there's dark matter. You still don't really know exactly what it is, but there's pretty much, just from these simple dynamics, simple Newtonian dynamics, people understand that there's dark matter. But it's not really known if it's hot, if it's cold, what its properties are, if it's like regular matter, like protons and electrons, or if it's very different. And then the early 80s really saw a boom in numerical techniques. And those numerical techniques ended up being very important because they were refined so that you could improve these n-body calculations and then test some of these different pictures, because you could give velocities to your particles in your calculation, and that would give rise to different structure. And they ruled out some structure. And at the same time, you also have people saying, well, what is the structure of the galaxies? So remember that the Friedmann solution applies to a homogeneous and isotropic universe. But look around. This is not homogeneous or isotropic. So what is the scale on which you get homogeneity and isotropy? And that scale is quite large, right? So you have to actually do a survey of galaxies out to very, very large scales in order to be in that limit where you can do the comparison. So it really motivated people to do the first redshift surveys. So this is a redshift survey led by Mark Davis in the late 70s. This is a very famous. These are galaxies. Every point in this pi shape is a particular galaxy whose redshift velocity is known. And you can see already this guy is called Stickman. It's kind of an iconic astrophysical guy. But you can already see there's this pattern of sort of filaments of galaxies, and then there are places where there are no galaxies. So there are these overdensities and underdensities in the galaxy distribution itself. And that's exactly what you predict from this simple linear theory. And of course, Jim Peebles went to the next level, and in 1982, he actually examined what this spectrum of fluctuations would look like if the dark matter is some cold particle. And so this is really the cold dark matter picture, and this just shows the amplitude of mass fluctuations as a function of scale. And you can just see you get this scale invariant. There's no preferred scale in this diagram. You just get this spectrum of fluctuations that turns out to look very much like what we observe today. So 20 years after Penzias and Wilson, finally, the COBE satellite is flown. You get a very precise measurement of the black body itself, and you also get a measurement of these fluctuations. And I'm just going to show you how you see these differences in temperature that are apart in 100,000. And now just going forward into the modern day, what WMAP and Planck actually looks pretty similar. You see these hot spots and these cold spots corresponding to mass underdensities and overdensities. These tiny, tiny little fluctuations, which now we can just study to death. We now can study the entire pattern of these fluctuations. We can learn a lot about physics in the very early universe, and we can learn a lot about physics in the later universe, like galaxies, which is where my stuff really is focused. So we're sort of in this era of precision cosmology, and I'm just putting up a montage. So you don't have to read the axes or understand these figures. But the thing that you need to understand is that there are lines in these figures, and there are data points in these figures. And the data points have very, very small error bars for the large part. And that really is telling you that we are in this era where we're measuring various different elements, different aspects of the cosmic microwave background to increasing precision and getting very precise cosmological parameters out of this. So So that's very exciting. But of course, I do want you to look at this figure here. If you look at the scale that I'm showing here, you see the microwave background is on large scales. And large scales correspond to small wave numbers k. It's 1 over the distance, 1 over the scale. And then you have something called the Lyman alpha forest at these small scales, and you have galaxies sort of in between. So that would be like Stickman. And then you have clusters, which are like those things I showed you at the very beginning. Okay? But this sort of peters out at around a megaparsec, h inverse co-moving. So what's happening below there? Okay? Just to show you where we are in terms of galaxy redshift surveys, this is an example from the Sloan Digital Sky Survey. I mean, you just see that whereas in 1980 you had Stickman, now you've got this incredibly beautiful and incredibly well fleshed out galaxy population, and they're color-coded according to their colors. So they're the types of stars that they have. And of course, from this microwave background and from these galaxy surveys, we now know a lot about the universe. We know that the largest portion of the energy density of the universe is in this dark energy, and then the next largest portion is in this dark matter, which we think is non-baryonic. And then only this tiny, tiny fraction of the energy density is in stuff that we understand, like protons and electrons and neutrons. But most of this normal matter is in hydrogen, and it's my favorite element. I've been working on it for a long time. It's very tractable. Doesn't give you any nonsense like iron. And something that I work on is this Lyman alpha forest and trying to understand this Lyman alpha forest. And why I'm interested in it is because it goes down to these scales where the galaxies, the individual fine-grained galaxy distribution really matters. And so you simultaneously have a link to cosmology and also a link to the galaxy properties. Okay? So what is the Lyman alpha forest? What am I saying? So imagine you have bright sources in the distant universe, and you have this filament void network that I showed you. And there's gas tracing that filament void network, but it's only a tiny tracer amount of gas, as I showed you with the densities. That gas is primarily hydrogen, and hydrogen is absorbing photons as they come from that distant source to you. So as those photons come toward you from the expansion of the universe, they get redshifted, and at some point in their trajectory, they are resonant with the hydrogen, and they get absorbed and scattered out of your sightline. And that creates this very tenuous system of absorption lines. This is the Lyman alpha transition from a high redshift quasar, and these are the absorption lines coming from hydrogen intervening between us and that quasar. And this looks kind of like a forest, so people called it the Lyman alpha forest. And it turns out that when we do calculations of structure formation, including gas, and we draw sight lines, we pretend there are quasars in our calculation, we draw sight lines through it, we get something that looks very, very similar to this. So it's actually a really great test of the picture. And I'm just going to show you one of the calculations that I do. So we're going to start at high redshift. I'm showing you the temperature of the gas. And we're going to come down all the way to the present day, starting from, we're not starting at the CMB, but we're starting at a high enough redshift that, that we can actually compute the calculation. And you see there these filaments, this temperature scale is shown on the right, or on your left. And pink means hot gas, and blue means cool gas. And we're going to zoom in to the center of one of these high overdensities, and that's showing you how stars and stars are they're forming in these calculations. They're giving off radiation. They are giving off metals that are cooling. And so I'm just going to show it one more time so that you can see it again. As this calculation proceeds, you see these galaxies are forming in these knots in this distribution. So these high density peaks, that's where the galaxies are forming. And all of this tenuous stuff is what the Lyman alpha forest is. It's this gas that's kind of yellow coated here, like maybe greenish. That's all the Lyman alpha forest. And these are galaxies and clusters of galaxies forming computationally. So they just form, we put the equations of motion in, we put hydrodynamic equations in, we evolve them, we say what the stars do, we say how much energy and radiation they give off, kinetic energy and radiative energy, and we compute this evolution. And we think this is a very well understood process. I'm going to skip over some of this because I want to make sure to get to black holes. But I want to show you where we have this really nice framework, but it sort of breaks down at this galaxy scale. So I told you we can calculate this spectrum of halo masses, so this distribution of dark matter masses for galaxies. And that looks like this, right? That's this Pressure picture, and that's this red dashed line. Okay, but when we go out to measure galaxies and we make the same diagram, this is just mass as a function of number density. Okay, they look like this blue line. So that's not a success. That's like a terrible failure. It doesn't even meet at one point. You can normalize it so that it meets at one point. So why does that happen? Why, when we go to these small scales, we have this beautiful success down to a megaparsec. Once we go to these nonlinear scales, our theory doesn't seem to be holding up very well. And the answer is all of that pink stuff that I was showing you just now. It's all of the baryonic physics, we think, that is happening in these systems. So at this mass, we think that black holes that are accreting are fixing this. They're basically making galaxies, they're making dark matter halos have less star formation. And here we think that supernova explosions are heating up the gas and not allowing it to form stars. And that's why there are fewer systems than we would just naively expect from cold dark matter. So we have this realistic cosmology, but unrealistic galaxies. And that's not so much of a surprise because we're not quite resolving phenomena like this. So this is a star called Eta Carina, which is a high mass star near its end of life. These are what we call the pillars of creation. These are star forming regions. In order to resolve these cosmological scales, it's very, very difficult to numerically resolve the scales of individual stars. And so galaxy formation is just very complicated, and we haven't actually figured it out yet. Each one of these dots in this large redshift survey corresponds to one of these galaxies that's either blowing up its gas or has a black hole in the center. And we don't know how exactly that match happens, except in the most basic sense. And of course, these are blowing gas out of these systems. We call these galactic superwinds, which is a topic of we're very excited about, because once we figure this out, once we figure out how to make the galaxies look real, then we'll have a realistic cosmology and realistic galaxies, and then we can really do sort of the next generation level of testing of cosmology, whereas right now we're sort of stuck. This feedback can affect the local environment around galaxies. So if you have these winds blowing and they're strong, they can make big hot bubbles around the galaxies. This is just a slice of the gas density for different simulations that I'm showing here. Anyway, this is just to show you that different models produce different things. And they also turn blue star-forming galaxies, or this one looks red because it has dust, into galaxies that are more circular and not forming stars anymore. Let's see. Our simulations are improving, but since in the interest of time, I want to just say things are getting better. So this is from a new suite of simulations where, it's starting to look pretty good. We put false colors in our simulations, and we kind of make them look like real galaxies. But the fact is we haven't really solved this problem yet, and we don't actually know what the solution is. So there are a lot of remaining puzzles. We don't know how galaxies in detail get rid of all this gas and how they form stars over time. We don't really know what the balance is between these supernova explosions or these quasars, these accreting black holes, which I'm going to get to right now. It could be some other physical process like conduction or other instabilities, and we don't really know. So one thing we really need to pin down is, do the galaxy properties, their sizes, their masses, their kinematics, do these look actually reasonable in this CDM picture? So since it's pretty close to the 100th birthday of general relativity, I couldn't possibly come here and not talk about the other sort of solution to Einstein's field equations, and that's the black hole solution. So this is, I work on these systems, and of course this is a very, very exciting time. Most of you know this. Why is it called a hole? Well, so it's called a hole because it's a mathematical singularity, so the density is infinite, space-time is infinitely curved. And black, in relation to thermodynamics, it behaves like a black body, so radiation doesn't escape. That's just the kind of standard picture here. There are two regimes of astrophysical black holes, and that's the black hole that I want to talk to you about today, not the quantum mechanical black hole, which are they're super fascinating, but I'm just going to stick to the astrophysical ones today. So there are sort of stellar mass black holes between 1 and 100 solar masses that are the result of the end states of stars, these supernovae that I've been talking to you about, sometimes leave behind black holes. Then there are these other black holes that are around 10,000 to 1,000,000 times the mass of the sun. And we actually don't know how these form. Right? We have a lot of ideas about how they form, but we actually have no idea really how you make, well, we have lots of ideas, but we don't know for sure how you make a million solar mass black hole or a billion solar mass black hole, especially because you see these very early in the history of the universe. So these black holes exist at very early times. What I think is really fascinating is that actually astronomers have been struggling with this notion from two very different perspectives for hundreds of years. So people debate this, but I think it's actually very deep. So in 1784, and then again in 1795, John Michell and Laplace just reasoned from Principia. They just reasoned from escape velocity, that if you had something massive enough, eventually its escape velocity would be larger than the speed of light. Now, they didn't really have a good idea of the speed of light, and escape velocity isn't really what's happening in the black hole. So you could argue that these aren't, that this notion of black holes is very different from the notion of black holes you get from solving GR. But I think the point is very similar. You're just taking this theory to its natural conclusion and asking, well, what are the consequences? We've only been confronting observations, black hole ideas with observations for the last 100 years. And that actually started with Vesto Slipher, who was in an attempt to measure these velocities that I talked to you about earlier to get this expansion, was measuring anomalously high velocities in the centers of galaxies. And he didn't understand why the velocity dispersion was going up in these galaxies. And so he thought maybe there was just increasing pressure, or the nucleus was somehow different. So in the nuclear part of certain galaxies, he noticed from the spectra that something looked very different. Now, when black holes feed, so you think of black holes as sucking things up, and in fact, we see black holes with accretion disks. They shine as quasars when they accrete matter, and we think that looks. Let's see. So for many years, this was the only way that people had any clue about black holes, like observationally. And that came from Don Lynden-Bell, who made the connection between the Schwarzschild solution and the quasars, because what people observed was just that they saw these quasars that had very, very high luminosities, very, very high radial luminosities and optical luminosities, and they were puzzled how you could actually get the energetics of that to work out. So when Martin Schmidt in 1965 publishes the redshift of 3C273 and finds that it's at a great distance, it implies a huge energy, totally in violation with normal types of stars or things that we understand. So observing quasars was the really only way we knew they existed. So Lynden-Bell proposes that these collapsed black holes really are the quasars. But actually, this idea, according to Lynden-Bell, most astronomers treated this paper with silence or disbelief. Where was the evidence? So it actually, unlike general relativity, really didn't, even though it solved this important problem about energetics that people had been really struggling with since the 50s, it was not accepted immediately, and it was very counterintuitive. So how could you produce so much energy? We have different types of ways of thinking about accretion onto black holes. So for astrophysical black holes, where we're actually measuring the luminosities, there's two basic types of accretion. There's sort of spherical accretion and this sort of disk accretion. And we don't understand these perfectly, so there's still real problems with these theories. But in the idea of an accretion disk, you have different temperatures at different radii. Each radius corresponds to a different blackbody temperature. And that seems to look like what quasar spectra look like. And so that idea of a disk of accreting matter seems to jive with our observations, at least at some level. Now, what about the Milky Way, right? So is there a big black hole in the center of the Milky Way? So people knew from basically right after World War II that the Milky Way was the center of the Milky Way was a bright radio source. but they didn't exactly know. They didn't exactly know what it was associated with. And even in 1993, so not that long ago, people did not think that you could even see curvature in the orbits of stars around the center of the Milky Way to determine if there was a black hole there. But in fact, it was the progress in infrared astronomy, so the fact that you could do adaptive optics on big telescopes and the fact that you had very sensitive infrared arrays that allowed you to see the galactic center very, very clearly. And of course, this is the result of that endeavor. There are two groups who worked on this. I'm showing the picture from the UCLA group. But you could actually watch stars in Keplerian over enough time. You could watch stars in Keplerian orbit around a central dark system. And the enclosed mass, if you calculate, they've got an orbit that actually closes, is about 4 million times the mass of the sun. And so this is really, in my mind, very powerful observation about, just very fundamental. I mean, from Kepler's laws, measuring this central dark mass and finding out that it is really one of these million solar mass beasts is very exciting. And we think that they're actually in all nuclei of galaxies. So every time we go to a galaxy and try to measure a big galaxy and try to measure something at their center, we find that there seems to be either a dormant black hole or an AGN. The quasar period is over. So if you look at the space density of quasars as a function of look-back time, so this is the present day, and this is well into the past, you find that now most quasars, there aren't really many quasars around, these accreting bright objects that I was talking to you about. Most of the black holes are dead by the present day. And of course, we can measure black hole masses in very large surveys. So this is a measurement I did a while ago. But this is black hole mass as a function of luminosity. And what was interesting in this study is that we found that that this relation clustered very closely to the Eddington ratio, which is sort of the maximum luminosity you can expect from one of these systems in sort of standard pictures. And now we actually have many thousands of black hole masses. What about these stellar mass black holes? So what about in the Milky Way? Well, so in cases where we can measure black hole masses, usually we want binary systems because we know how to handle Kepler's laws. And so if we have black holes with neutron stars, these are sort of the remnants that we can measure. And you can see that neutron stars sort of cluster around 1.5 solar masses, which is not surprising. And the black hole masses that we've measured in the Milky Way, they seem to be kind of spread between, I don't know, 3 and 10 solar masses. Okay? Where are all the ones in between? So, these are like 3 solar mass black holes, and these are like the ones that I measure up there. Where is Ant-Man in this, in this picture? What is the actual real spectrum of black hole masses? But of course, many of you know that this field is in the process of major revolution. So of course, it was just announced that on September 15th, the LIGO experiment for the first time detected gravitational waves using the Michelson interferometers, the fancy Michelson interferometers at Hanford and Livingston. And what they saw, this is the signal that they saw. Of course, this is the waveform cleaned up a little bit. And this is the frequency, this chirp that many of you guys have probably been hearing about. And it's really hard to overstate how important this measurement is and how exciting this measurement is. And why do I think it's so important? LIGO was, for many, many years, so LIGO has been going forever, and it's been working so hard for so many years. But a lot of people were really interested in finding neutron stars or stars that we can actually probe in other ways. But black hole mergers of this type, of the type that LIGO actually found, cannot be probed in any other way. And so, or at least we don't think so yet. Might be that there's an electromagnetic counterpart, but we actually don't know that. And so this is just a totally, when people say this nonsense about we've opened a new window, it's just a total lowball. They've like blown the side off a house. It's not opening a new window. That's not what's happening here. It's just much more significant in my opinion. And just to show you, I showed you what we thought of the these are the black holes we know about in the galaxy aside of this supermassive system. They're just little black holes. And what was observed were black holes of 30 solar mass apiece. Right? So this is what was predicted based on, this is the chirp mass now. This is what was predicted, which is a combination of the masses, the individual masses. This is what was predicted in 2012 for what these masses should be. And you can see there's this sharp cutoff. And you can actually see that for, when they actually do more careful modeling at this redshift, they find that actually the peak of this distribution, even though they can produce things up to that mass, the peak of this distribution is kind of around the mass that we saw for the Milky Way black holes, around 6 solar masses. And then here's the detection. So it's just not in line with these predictions at all. And so I think that's really exciting. We're waiting for more events, trying to understand them. We're trying to understand, we're just trying to get every detail out of the one event that has been released by the LIGO collaboration. But this is just a totally new way to probe the universe. And for the supermassive black holes, like the kind that I mainly measure and work on, something like a new interferometer in space that has more sensitivity or at different frequencies, would be able to test how often you get those mergers. So that's very exciting. So I'm just going to end here on a sort of philosophical note. So Kant really had this idea that that space and time weren't real things, that they were sort of, there's some observer. There are sort of constructs that we sort of organize our perceptions of the world, and it's just some appearances that we operate in. But I would say that the observation of black holes and the inflationary universe, that really kind of destroys this notion. These are ideas that came just out of mathematics and out of people's minds, and then we found them. They're real, they exist, we've measured them merging, we've measured their masses, they're real things, and they just came out of people's thoughts, following the mathematics to its final conclusion. And so I think that's very different. I think that's a real rebuke of Kant. I mean, he got some things right. I mean, he's not the worst, but I think he was really wrong on this. OK, so I just want to say thank you, and I'll take any of your questions now.